This section is on counting sample spaces. I think in the last video I went over an example of tossing a coin 4 times and listed out that sample space. In this one, what if we were to toss a coin 3 times and separately record the outcome of each toss? So I want to know what the size is of the sample space. Well, first let's actually list out the sample space. So what I could have is heads, heads. Okay. There's no super quick way to do this. We just have to list everything out. We could have heads, tails. We could have heads, tails, heads. And we could have tails, heads, heads. Notice I just listed out the scenario where it's all heads, and then I listed out all possible scenarios where there's only one tail. Okay. Next we can do about heads, tails, tails. So these are all now the scenarios with 2 tails and 1 heads. So how about heads? That would be the same thing. We could have tails, heads, tails. And we could have tails, tails, and heads. Okay. And you can think of it the other way. That's the scenarios where there's 1 heads and then there's 2 heads over here back in the center. And the only other option would be all tails. Alright, so it's 1, 2, 3, 4, 5, 6, 7, 8. So N is the sample size, or the size of the sample space in this case, so there's 8 different possibilities. Suppose now we toss a coin 10 times. So this is just one of the many possibilities that could come out of that. So you could start a tree diagram to do this. So let's say we go up here and we say, okay, well, it's either heads or tails the first time. Okay, the second flip, that's either heads or tails. Or if the first flip was tails, the second flip can also either be heads or tails. Branch out from there. Heads, tails. Heads, tails. So you get the idea. It kind of branches out just like a tree. And in this particular example, it would be tails, heads, and then heads just following everything up here. But this is going to take us a while if we wanted to see all the possibilities. There's another way to at least find the number of possibilities a little more quickly. So what we can do is list out, I like to call them boxes or slots for each possibility. So for example, the first slot. So the first time I flip, I can either flip a tails or flip a heads. So that's going to be 2 possibilities there. The second time, I flip again. It's either heads or tails. The third time, once again, it's either heads or tails. The fourth time, it's either heads or tails. And it's important to note that these events are independent. Just because I got a tails the first time, that doesn't have anything to do with whether I'm going to get heads or tails the second time. So we keep doing this until we get to the end. So 9th time where it's either a heads or a tails, so 2 possibilities. And 10 times, once again, either heads or tails. Okay. So how many different ways can this be organized? Well, what's coming up next is called the multiplication rule, and that's just when you multiply all the possibilities together for each round. So for example, I would say 2 times 2 times 2 times 2 all the way up here, 2 times 2. So there would be 10 2's multiplied together, so it would just simply be 2 to the 10th power. And more specifically, n is equal to 2 to the 10th power. So that brings us to the multiplication rule. So when something is done in stages, the number of ways it can be done is found by multiplying the number of ways each of the stages can be done. So going back to that coin example, and sorry the way this came out on the screen doesn't look right, so that should say 2 to the 10th. So toss a coin 10 times, just 2 to the 10th power, and get 1,024. Our next example here deals with different combinations of putting a wardrobe together. So Dolores is a young saleswoman planning her next business trip. She is thinking about packing 3 pairs of shoes, 4 skirts, 6 shirts, and 2 jackets. How many different outfits can she create? Uh, Problems like these usually pretty simple, so we just take everything 3 times 4 times 6 times 2 and multiply it together, and you'll get 144 different outfits in the end. So now we're dealing with a similar example. So this time Dolores is planning her next business trip, but this time she's packing 3 pairs of shoes, 4 skirts, 3 slacks, 6 shirts, 3 turtlenecks, and 2 jackets. How many different outfits can she create? This time it's important to note that we can't just multiply everything together by saying 3 times 4 times 3 times 6 times 3 times 2. It doesn't work that way because specifically looking at what we'll call, I guess, the lower wear, skirts or slacks, those aren't typically worn together, so we'll treat them as separate things. So that's where it comes with, well, first of all, shoes are separate from everything. Okay, so the 3 pairs of shoes. Then we have skirts and slacks. Okay, and typically she's only going to wear a skirt or a slack and not both. So we'll just add those possibilities together, and that's going to make 7 total. So same thing with, let's pretend in this example at least that she picks to either only wear a shirt or only wear a turtleneck but doesn't wear both. In that case, we will be adding the 6 and the 3, okay, to make 9 possibilities for that outfit. And then in the end, just the 2 jackets goes here. So that would, in the end, be 3 times 7 times 9 times 2, which should come out to 378 possibilities. We're changing it up here one more time. This time, still have 3 pairs of shoes, and skirt and slacks are still treated differently. But let's say that she does have the option of wearing a blouse and a turtleneck, or just a blouse or just a turtleneck. So looking at stage 3, that's where everything becomes a little different here. So the 6, where it says blouse, so just a minute here, let me get the highlighter. I'll just circle it. So this 6 right here, that represents the 6 possibilities of just wearing a blouse. So the 6 shirts available. And then the 3 represents the 3 possibilities of just wearing a turtleneck. But then the 6 times 3, let's say that she chooses to wear a blouse and a turtleneck. Well, those are all the combinations of ones we could put together. So we're going to multiply the 6 by times 3, but also add the options where she chooses to wear just one of those items. So we're going to say 6 plus 3 plus the result of 6 times 3, so that's 18 plus 3 plus 6, 27 total options for upper wear. And in the end, we'll just multiply everything together, and ultimately she's going to have 1,701 different options as far as her wardrobe goes. Alright, this next example isn't quite as complex. We have 5 candidates, A, B, C, D, and E, are running in an election. The top 3 vote getters are chosen president, vice president, and secretary in that order. How many possible combinations are there? And notice that this problem says in that order. This is a problem where order matters, and you may have seen this in another class before, maybe not. And it does pop up in discrete math at some point. Combinations, we usually, mathematically, when we talk about combinations, we just mean grouping things together. The proper word for when order matters is actually called permutation. So I'm going to cross this out. Instead of saying how many possible combinations are there, I'm going to say how many possible orders are there, or we'll say permutations, just so we're mathematically speaking correctly. But anyway, so for president, that's the first thing that's available. Well, there's 5 people running for president, so I'm going to put a 5 in this box. After somebody wins president, let's say, for example, candidate C wins president. Well, we need a VP, and candidate C cannot be both president and VP, so that leaves 4 other options to possibly be the VP. So 4. And let's say that candidate E gets the VP. So C gets president, E gets VP. Secretary, by that point, neither of those candidates can be the secretary also. So there's either A, B, or D will win the secretary position. So there's only 3 options or 3 possibilities at that point. Okay, and then in the end, you're just going to add everything together. So 5. Oops, I mean multiply everything together. So that'll be 5 times 4 times 3, so 20 times 3, so that would be 60 different orders or 60 different ways we could put people in these offices. Alright, next, a computer password consists of any 5 capital letters from the ordinary English alphabet, so A through Z. How many different passwords are there? So what I'm going to do is create boxes or slots here for the possibilities. It's 5 capital letters, so okay, so 1, 2, 3, 4, 5 slots. For the first slot or first box, I have 26 letters to choose from, so it's just going to be 26. Now, it doesn't say that we can't repeat letters at all, so if my password just wanted to be E, well, then that could be a password. So I could choose the same letter all 5 times if I wanted to. So anyway, the point of that is that it's going to be 26 all the way across the board. Alright, so our final answer says how many different passwords are there? That'd just be 26 to the 5th power. Which comes out to about this really big number here. So 118. So over 11 million, almost 12 million. Next, how many passwords are there if no letters repeat? So this is a very different scenario. So we still have those 5 letters, so there's 5 slots or 5 boxes. Okay, now the first time there's 26 letters available. Now if no letters repeat, say for example we picked the letter D. So if I use letter D, then can't reuse that. So then I would need to choose from the other 25, for example. Okay, and then maybe the next time we pick Z. If I use Z, I can't reuse D or Z, so I would need to pick from the other 24. So every time you use one, there's one less available. Okay, so in the end, it would come down to 26 times 25 times 24 times 23 times 22. And that's going to be a little bit less. That's going to come out to, let's see, 7, 8, 9, 3, 600. Alright, so 7,893,600 possibilities there. In this example, a license plate from Hazard County consists of 5 alphanumeric characters. So By that we mean either letters or numbers. How many possible license plates are there? So notice it doesn't really give us any rules about whether or not letters or numbers can repeat, so we'll just assume that they can. So there are 26 letters possible, and there are 10 digits possible, 0 through 9. So we'll add those up to make 36. And if it's 5, it would just be, let's see, 1, 2, 3, 4, 5. We're going to assume that we can repeat, so 36, 36. So pretty much just 36 to the 5th power. And that is going to come out to be over 60 million different possibilities.